So as a little review, oops, that doesn't look very good. I was playing with this. I probably shouldn't have been. Let's see. Oh, no, not pink. Not black. No. That looks really bad. I'll see if I can fix that. Oh, come on. Well, I'm sorry. We'll just have to deal with that. Light line. Okay. So review. So when we were talking about the elements, what was the mnemonic device I gave you? Schnapps. Okay. So one of those elements was nitrogen. Okay. So in the periodic table, the atomic mass of nitrogen is 14. So how many protons does the and neutrons does the nitrogen atom have? 7. Okay. This is the atomic number. This would be the number of protons. And so how many, this is a neutral element, how many electrons does it have? 7, right? So if we were to draw the nucleus, okay, how many electrons are in my first shell? 2. So how many electrons would be in the second shell? 5. Oops, electron. Okay. So is that outer shell filled? No. So how many electrons could it hold? 8. And so how many is it going to want to share? 3. Okay. So for example, ammonia is N H3. So this is ammonia. Okay. So what does this solid line represent when you're looking at a molecular formula? What type of bond? Covalence. So the covalent bond is a sharing of electrons. And so the hydrogen is happy here because it's sharing an electron, and so its outer orbit is filled with 2. The nitrogen is happy because now instead of 5 electrons, it has 8 in its outer orbit. Now, what do you think about this molecule? Is it going to be polar or non-polar? Which one is stronger? Which one has more protons? Nitrogen or hydrogen? Hydrogen's got 1 proton, right? So what's going to happen is that it is going to draw the electrons towards itself, right? And so this is going to be, that would be an example of a polar covalent bond. Because it's going to be slightly negative and the hydrogen is going to be slightly positive. And so there's polarity to that. So that's kind of a review of the information that was in that lecture that was reported online. So let's look at energy as it relates to atoms and how it relates to molecules. So when we talk about energy, energy can be defined as the ability to do work. So we have some energy that is stored, and it is called potential energy. But the storage of energy, the stored energy, this potential energy could be converted to another form of energy, okay? So if it is doing work, then it is called kinetic energy. So within the atoms, we can store energy, and the energy is stored in the electron and the distance that the electrons are away from the nucleus of the atom. So I'm going to draw my little nucleus here, and then I'm going to draw these shells around it. Okay, they would go all the way around it, but I'm just going to draw them just halfway around it. Okay, so this is my nucleus at the center. Here I could have an electron, and then I could have an electron out here. Okay. So remember that the electrons are negatively charged and the nucleus is positively charged. So if I move this electron further away, it is a lot like moving two magnets apart. So I would have to put energy into it, so it would take energy to move it further away, right? But it would then have stored energy. So if I drew my line from this shell, this orbit, to this one, right, I would say that that is stored energy. So I'll put stored energy. So now it has potential energy, so that if it then goes back towards the nucleus, it could release that energy. Okay. If the electron goes the other way, so if it goes from here, right, towards, then you're actually releasing some energy. So I'll put this as releasing energy. So this is actually the way that plants are able to capture light energy. So photons come in, and the plants have these little green structures called chloroplasts, and they have chlorophyll in them, which is a molecule that when sunlight hits, it causes the movement of the electrons, and so the chlorophyll then kind of takes that light energy and it stores it, and then it can use it to do work, right? So it actually stores it and it uses it to build sugar molecules. Okay. So in much the same way that we can use stored energy as well. So if we think of an example of a molecule that we use as energy, we could look at the example of propane. Propane is an example of a hydrocarbon. It's actually a fossil fuel. So in order to get the propane had to be a part of, we might not make propane, but in general, fossil fuels are derived from old vegetation that has been then converted into types of fuels that we can then burn and release heat, okay? So propane actually has lots of potential energy in it, and this type of energy would be chemical energy, and it can be stored. Oops, I didn't want to put that way, sorry. And it can be stored. Okay, so propane is C3H8. So what that means is that there's 3 carbon atoms, and they are covalently bonded to hydrogen. So that's why it's called a hydrocarbon, is that there's nothing but hydrogen atoms and carbon atoms. Now, when you burn propane, you need a spark, but you also need oxygen. So we combine this with oxygen, right? And this is a form of combustion where we're going to break apart the propane, and we're going to produce, as a byproduct, carbon dioxide, right? And we're going to also produce water, and we're going to produce heat. So this heat is energy. So when I break the bonds between these carbon, the electrons move in towards the nucleus, and they release energy as heat. Okay? So this chemical reaction requires a little bit of energy to start it, and then once it proceeds, it actually produces more energy than it actually uses. And so this is an example of what we would call an exergonic reaction. So this produces more energy than it uses. Oops, produces more energy than it uses. So the energy between those, in those covalent bonds, the electrons move, and that causes heat to be released. Okay. The opposite of exergonic is endergonic. And this requires more energy than it produces. Okay, so ender means that energy has to come in and it's absorbed by the chemical reaction. Exergonic is energy is released. Okay. So from your lecture, would this be an example of a catabolic reaction or an anabolic reaction? Anabolic. Is it building something or is it breaking something down? It would be catabolic, right? Because it's breaking down propane in the presence of oxygen and it's producing small molecules, right? So this would be an example of catabolic. Right. Catabolic usually is exergonic versus anabolic, which is building stuff, building molecules, and that usually requires energy. So it required energy to put those carbon atoms together, and it releases energy when you break the bonds between the carbon atoms. Okay, so you could put down here, catabolic is usually exergonic, and anabolic is usually endergonic. So this would actually be an example of a chemical reaction. It's not balanced because there's not the same number of carbon on this side as to this side, but this is an example of a chemical reaction. And so that's what we're going to talk about next, is chemical reactions. So when we talk about chemical reactions, we can talk about all the reactions in our body, which is our metabolism, right? So this is all the chemical reactions in our body. So when you talk about a person's metabolic rate, how would you go about, or how do they generally go about trying to figure out what your metabolic rate is? Like to estimate how much metabolism is going on in your body. Well, at rest. So if I wanted to find out if my metabolic rate was higher than your metabolic rate, what would you do if you were doing it at rest? How much you breathe, right? And so what they do is they estimate the metabolic rate by the amount of oxygen that is consumed. As just a squiggle. Metabolic rate by the amount of oxygen consumed or taken in, right? So if you had something really fancy, you could actually measure that. You could measure also the amount of CO2 produced. But you could just look at breathing rate. So if I'm running, my metabolic rate is going to be higher than if I'm just sitting down because I'm consuming more oxygen, right? And that just tells us how important oxygen is in producing energy and then providing energy for all the other chemical reactions that have to take place in our body. So when we talk about chemical reactions, we can talk about the reactants, right? So these are called the reactants. And this would be the product. Is this a chemical reaction? Is this catabolic or anabolic? Anabolic, right? So it could be like A and B are amino acids, right? And I put them together to make a polypeptide or a little connection between the amino acids, right? So that would be an example of a anabolic chemical reaction. Now, sometimes we have to have things that speed up the chemical reaction. And this is what are referred to as enzymes. So this could be an enzyme. And the enzyme is a chemical that speeds up, or we'll put molecule, sorry, molecule that speeds up the chemical reaction. Most of the enzymes in our body have an ending to them, which is ACE. So for example, one enzyme that we're going to look at is an enzyme called lactase. Okay. So ACE, whenever you see ASE, that is an enzyme. However, there are some enzymes that don't end in this. So there's a stomach enzyme called pepsin, which breaks down amino acids and breaks their peptide bonds, and it's called pepsin, and it doesn't have the ACE in it. But if you see the ACE, that means that it is an enzyme.
So all ACE equals enzymes, but not enzymes or anything.
Yes. Yep. Okay. So what do you think lactase, what do you think it does? Just looking at the word. Breaks down lactose. Okay. Oops. Ran out of my room here. Okay. So lactose is milk sugar. It's a simple, relatively simple milk sugar. It is only composed of 2 sugars. So lactase breaks it down and it produces glucose and galactose. In week 3, there is a homework that you need to download, and you want to watch a video, and it's going to talk about what is referred to as lactase persistence. Because we are mammals, when we're newborns, we rely upon milk for nutrition, breast milk, right? And we produce this enzyme in our intestines that helps to break it down. But most mammals, when they go through weaning and they stop drinking milk, they stop producing this enzyme. And so the question is why are some populations of humans lactase persistent, which means that they're still able to break down lactose even as adults, even when milk isn't a primary source of nutrition. And so that is going to be a homework assignment. You're going to look at it in terms of, it is an example of an adaptation in certain populations of people on the planet. Okay, so that is just right, homework. And it's not due till the end of next week. Okay, so we could ask, how do these enzymes do the work that they do? And so we can look at the shape of an enzyme. Oops, I don't have a good picture of that. So this is a diagram from your book that shows the amount of energy it takes to take two reactants and produce a product. The exact same thing would be the case if I had, if I wanted to break down the product into its reactants. So you notice that with an enzyme, it takes a lot of energy to do that. So, I mean, you can add really a lot of heat perhaps and break it apart, but at normal body temperature, it wouldn't be broken apart or put, in this case, put back together. So this would be an example of anabolic chemical reaction. But the point here is the amount of energy that it takes for the chemical reaction to occur. So you notice that without the enzyme, it takes a lot more energy for the chemical reaction to occur than if the enzyme is present. So once the enzyme is present, then there's less energy required, and so it will speed up the chemical reaction. So there's one of the interesting things about the enzyme is that it's not used up. So enzymes will bind to the reactants. They'll cause the chemical reaction to be completed, and then they'll unbind, and then they are still present, and they can go on to the next one. So they just kind of move around, helping things either come together or break apart. So that's the significance of the enzymes. So we're going to be looking at that in lab this week. Okay. So we're going to move on to looking at water, and specifically looking at acids and bases and their significance. So when we talk about acids and bases, we oftentimes use what is a pH scale. And this pH scale doesn't have any units, but it goes from 0 to 14. Okay, so that's the scale, 0 to 14. So halfway through there is a pH of 7, and so we define the pH is the pH of 7 is neutral. So what the pH actually measures is the concentration of hydrogen ions in solution. So that is concentration, just abbreviated there. Okay, measures concentration of hydrogen ions in solution. Yes?
Is that what the H is for hydrogen?
You know, I don't know why they put the H. I don't know why. I think that is. Yes. So I'm not sure what P stands for. I'm not sure where they came with that, but yeah, that kind of makes sense. Yeah. Good way to remember it. Okay, so if we look at the water, water actually exists in two forms. Okay, so that's why I drew this arrow going in both directions. So what it means is it kind of goes, it's like this, but then it's kind of like this, and it just kind of goes back and forth, and there's an equilibrium to it. It goes back and forth, okay? So a pH of 7 is the concentration of hydrogen ions in pure water. Pure water is not tap water. Tap water's got other things in it. It's kind of like, tap water is more like spring water. So if you were to go to buy spring water at the grocery store, there are, they're like minerals and stuff in it, right? So tap water has chlorine in it, bacteria, and it has other things in it. So this is pure distilled water. You can buy pure water at the grocery store, and it's called distilled water. Okay. So that's the definition of the neutral, is the amount of hydrogen ions that would be in pure water. Okay. Now, the acidic range, this is kind of backwards. So if I look at the pH and it is less than 7, this means that it is an acid. So if it is 6, it is acidic. If it is 4, it is acidic. Okay. If it is 2, it is very acidic. Okay. So what that means is that acid is a chemical that releases hydrogen ions into solution. So does anybody know what kind of acid does our stomach produce? What is the name of it? What is it? That's bile's different. Bile's the yellow stuff that when you, yeah, the bile actually breaks down fats. So hydrochloric acid, okay? So HCl, this is hydrochloric acid, right? HCl is a very strong acid, and so it tends to dissociate like this. So the stomach, your stomach acid could be like a pH 2, right? It can be really acidic, and that is actually very protective because when we take in food, it has lots of microbes on it, fungi on it, even have parasites in it, right? And hopefully our stomach acid would kill all those things that might cause us disease. And the acid also helps to break down the protein. So it helps to break down the protein if we eat a steak. A really acidic stomach will help you to digest that steak more efficiently than if your stomach's not very acidic. We can actually mess with the acidity of our stomach, and a lot of us have to do it. We have chronic heartburn. The acid gets up into your esophagus, right? And so you can take acid reducers like Prilosec or Zyrtec or those kinds of things, and that reduces the acidity in your stomach. So it actually makes you more prone to getting sick from food poisoning. But it also protects your esophagus because you're not having heartburn a lot. And that can heartburn, chronic heartburn or chronic acid in your esophagus can actually lead to esophageal cancer. So it can be a bad thing. Okay, so that's an acid. And its pH is really low. It's below 7. It's actually more of a pH of 2. Okay. If we look at if the pH is greater than 7, then it is alkaline or a base. Okay, so if you say something's basic, that means it has a pH of over 7. And alkaline is just another word for that. Okay, so an example, or if we look at what this does, this removes hydrogen ions from solution. Removes. So an example of a really common base that you probably even have in your kitchen is what? What would this be called? Sodium hydroxide. And this is baking soda. Baking soda is a weak form of sodium hydroxide, but it's a base. So this is sodium hydroxide. Okay. Releases sodium, and it releases hydroxyl ions. Right? So this is called a hydroxyl ion. This would be a sodium ion. Okay. So if this is in water, we have to think about what is happening. So water is releasing hydrogen ions, right? And so the hydrogen ion is going to actually combine with the hydroxyl ion. Oops. Okay. So this is going to combine with this, right? And it is going to form water. Now you can actually use baking soda. I wouldn't recommend using it a lot, but you can usually actually use baking soda. You can stir it in water, right? And you can use it to cure your heartburn. If in the middle of the night you wake up and there's nothing else in the house to do this, right? The problem with baking soda is that if you look at this, what's going to happen is that you're going to remove the hydrogen ions right, by taking baking soda. And then you're going to produce sodium chloride, which is what? Salt, right? Salt is not a very good thing to take in large amounts, right? Because it destroys your stomach, it causes your stomach to bleed. And it also will elevate your blood pressure because it will cause water retention. And so sodium hydroxide or baking soda is not the best heartburn medicine. Tums, for example, instead of sodium, it has what in it? You're going to use Tums instead of baking soda. What mineral does it have in it? Calcium. It's actually calcium carbonate. And so the calcium combines with the chloride, and you actually can absorb that, and you can use it to build bone, right? So calcium, Tums is a good thing to use because we all need probably more calcium. Calcium is important in many different ways in your body. Okay. But this is the idea of acids and bases. Any questions about that? So if we looked at the pH of your blood, oops, it is about a pH of 7.45. So is that acidic or basic? Basic. If we looked at the pH of your sweat, it can be like a pH of 5. So is that acidic or basic? Acidic. So our sweat tends to be acidic because that actually helps protect us from infection on the outside of the body too. It's called the acid mantle. And it actually keeps fungi from attaching to your skin and growing and developing. It's really good protection. Okay.
Is that word, one word, hydroxy?
Hydroxyl ion. So that's 2 words. Hydroxyl is the group, and that it has a negative charge, it means that it's ion. Okay. So in your textbook, they have diagrams up here of what happens when you add acid to water. The hydrogens, ions dissociate, right? If you add base to water, you get more hydroxyl ions, right? Which would then remove the hydrogen ions and make the water more basic. The interesting thing about bases is that they can burn just like acids. And so a really strong base can actually burn your skin as much as a really strong acid. So you have to be careful with both of them. That's an example of a really strong base. Well, you can get sodium hydroxide, which is really strong. So in its most concentrated form, you would want it to get on your skin.
So what is it used?
It is used in chemical reactions for synthetic, like if I was going to be a chemist and I was going to make stuff, I might use it. That's not used in the body. No, we don't have strong acids in our body. Probably the strongest acid we have in our body is hydrochloric in our stomach. That's the strongest acid. Okay. Okay, so let's talk about some characteristics of water that make it significant from a biological perspective. Okay. It has what is called a high heat capacity. And what this means is that it takes a lot of energy to change it from one form into another. So for like from a liquid into a gas, it takes a lot of energy to change that. Okay. So an example of that is it takes a lot of energy to convert from a liquid into a gas. And this is actually where we get the idea of a calorie. So a calorie is a unit of measurement where you have a certain amount of water, I can't exactly remember, and you have to convert it, a certain amount of water into a gas, and that's how much energy it takes to do that conversion. Okay? So in terms of energy, you could talk about calories in terms of energy in the body. Okay? So one way that this is important is that we can use water for evaporative cooling. And we are actually very unique in mammals because we have so many sweat glands, right? We have sweat glands all over our body. We think about dogs and cats, for example, or even birds. They're not mammals, but they also kind of pant, right? They actually have to cool by panting, and what a pain that would have to be. I would hate that. So we just sweat and we cool off, and it's kind of a great thing, right? So evaporative cooling via sweat. So what that means is that we put water on the surface of our body. It absorbs the heat from our body. That heat from our body turns that water into vapor, and the heat is dissipated. And it's quite the amazing thing. So that is an example of one characteristic of water. Now, the reason why water has this characteristic is that we have hydrogen bonding. So this is, many of these characteristics are due to hydrogen bonds between water molecules. Okay, so the hydrogen bonding between the water molecules. So remember that those hydrogen bonds are not the covalent bonds that we see here, right? But they're the dotted lines, right? So in order for water to go from a liquid to a gas, you have to break all these dotted bonds. These are the weak bonds. They're due to negatively charged polar molecules, right? But we have to break them all to get them to go into gas. The other thing is that we already talked about this, but I'll go over it again, is that it is a universal solvent, right? So it draws things into solution. And this is due to its polarity. So we can talk about a water molecule as being polar. So they can pull apart molecules and bring them into solution. Right? So this would be like if you took a sugar cube and you put it in water, what's going to happen is that the water molecules are going to be in motion. And they're going to be moving around the sugar. And pretty soon the sugar molecule, the cube of sugar, is going to start to break down. And pretty soon it's going to be all on the bottom of the beaker. But if you leave that beaker there long enough, pretty soon, just because of molecular movement, it has nothing to do with like putting energy into it or heating it up or anything. What you're going to have is you're going to have diffusion of the glucose, and you're going to get it equally distributed throughout the entire beaker. Okay, so the water molecules are going to move, and they're just going to pull the glucose molecules apart until glucose goes into solution. So that's how we carry, that's how we transport glucose to our nerve cells in our brain for energy. It's also how we transport amino acids. It's how we transport hormones. Lots of things are transported in solution, okay? And it's due to the polarity. And so the polarity can be shown by, remember, putting little positive and negative signs here. So it's the polarity that pulls the molecules apart. Water molecules are also cohesive and adhesive. What this means is that they adhere to one another, and they also adhere to other structures, right? So when water is moving through very small vessels called capillaries, they're actually kind of adhering to the capillaries, or maybe even in the veins, they're adhering to the sides, and one molecule is to another, and it just kind of pulls it. So this is really important for the movement of water through very small vessels. So this is important for movement of water. And this is called capillary action. Okay. And you can actually see this if you have a paper towel and it gets wet. Pretty soon the water will just be moving across the surface of it. And that's because as the water adheres to the napkin or the paper towel, it's going to drag along other water molecules, right? So just via capillary action, the water molecules move through the paper towel. Okay. So the same thing happens in the body, and it's due to their polarity. So again, they're cohesive and adhesive because they're polar molecules. And finally, one thing that's interesting about water is that it is less dense as a solid than as a liquid. And so what that means is that when water freezes, it actually expands. So you probably have all experienced this with putting your can of Pepsi or can of soda pop in the freezer, and you go back and it has exploded, right? And that's because when it froze, it caused the can to crack open and then everything came out, right? And so that's because it expands as it freezes. Now this is not necessarily good from a physiological point of view, but from an ecological point of view, it's really important because what this means is that if you take a lake or a river, water or ice will float. So it forms the ice, and the ice floats to the surface, and then insulates the pond or insulates the river, and it keeps it from freezing solid through. So it keeps liquid water, so bodies of water don't freeze solid in the winter, and it generally means that it insulates the liquid water underneath. Okay, so from an ecological point of view, that's a significant characteristic of water. Okay. So this is just an image that shows how it can pull apart a crystal of salt, in this case, not sugar, but it just pulls apart because of the polarity of the molecule. And it pulls the sodium and the chloride into solution. Now, water can also be used, and it is actually produced in some chemical reactions. So we'll put 5, right? I'm on number 5, aren't I? Okay. So it is important in chemical reactions. Okay. So this first one is called dehydration synthesis. Synthesis means to build, to put together, and so this would be anabolic, right? So we're going to build something. So you notice that these two units, these two reactants, have molecularly covalently bonded to them an OH group and an OH group. And what you can do is that you can take away water. So notice that this is a molecule of water. So you can dehydrate it. You can take water out, and then you can get a linked bond occurring between the two reactants. Okay, so this is anabolic. Water is removed. Product is produced. So water is actually produced in this. The second one shows what is called hydrolysis. So hydrolysis is the opposite of dehydration. So hydrolysis is added. So think water, hydro. Lysis means to break apart. So this is catabolic. So in this case, water is added. So water has to be present. So this chemical reaction would not occur if it wasn't in water. So our chemical reactions or metabolism occur in water. And water can be an important molecule, the source, right, to add to the reactants, right, the products. This would be the reactant. This would be the two products. Okay. So this means that water is used to break apart a molecule. Okay, so water is not removed, but it's added. So hydrolysis and dehydration are two opposite types of chemical reactions that use water or produce water. Okay. So the last thing I want to talk about would be a little bit of organic chemistry, just so that we have some idea of what we're doing in lab this week. And then the rest of the organic chemistry I'm going to post. So whatever we don't get through today for chapter 2, I will post it online and you should watch it by next week. So when we talk about organic chemistry, we say that it is carbon-based. Okay. So organic is versus inorganic. So for example, HCl, hydrochloric acid, that is an inorganic molecule. It is not carbon, it's not built on carbon, using carbon, right? Propane, however, is an organic molecule because it's based upon a chain of carbon atoms that are covalently bonded to hydrogen. So we sometimes say that we have a skeleton of, I'll just put this, of carbon atoms. And this skeleton could be a chain, or it could be a ring. So for example, I could have a ring of carbon atoms that looks something like this. Right? And this could be my organic molecule. Now these carbon atoms are not happy. So what they could be is you could have hydrogen covalently bonded here. And then you could throw in a couple of double bonds here, here, and here. Okay. So now notice that carbon is sharing 4 electrons. This has got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay. So this, I think, this is called benzene. You don't need to know that. But oftentimes when they draw organic molecules, they leave out the carbon and they leave out all the other elements that are covalently bonded. So you might see shorthand, it actually might look like this. This is the same thing as that, right? That's the same thing. Okay, so just because it's kind of tedious to draw in all the carbons, so every time there's a little joint here, a little angle, that means that there's a carbon atom there. And then we could draw in those double bonds. So there's one here, there's one here, and there's one here. So those two things are the same thing. So if you get into organic chemistry, you end up drawing a lot of figures. Okay, so from the skeleton of carbon, then we have functional groups attached, right? So we also have functional groups. Oops, functional, that says functional groups attached. And this gives them the skeleton of carbon, how this is actually determines how it interacts with other types of molecules. So for example, we could have an amine group. So we could have nitrogen attached with 2 hydrogen. So this is called amine group. Right? So this nitrogen could lose a hydrogen and become a little positive, and that would be an example of what happens with amino acids. So amine groups are found in amino acids. So amino acids have an amine group on them. Okay. We could also have an OH group, and that's called a hydroxyl group. And this is found in alcohols. So alcohols like ethanol would have an OH group on it. And so what tends to happen is it loses this hydrogen and then becomes a polar molecule and then interacts. So that's a hydroxyl group. So those functional groups actually determine how the molecule works and what it does. So this is an example of another functional group. You don't need to know this. This is carboxyl. This is an amine group. This is another carboxyl group. Okay. This would be hydroxyl groups, right? And so those all give the molecule its specific characteristics. So when we look at organic molecules, there are 4 groups. There are the carbohydrates. And so these are sometimes referred to as the sugars. So lactose would be an example of a carbohydrate. We also have lipids. And so lipids are very different from other types of organic molecules because they tend to not be attracted to water. They're actually repelled by water. So if you think about fat, if you mix oil and water, they do not mix. It does not dissolve. It does not go into solution, right? So lipids tend to be not water soluble. We then have proteins. Proteins are water soluble. Lots of our enzymes are examples of proteins. And then finally, we have nucleic acids. So our genetic material is an example of a nucleic acid. So DNA would be an example of a nucleic acid. So in the lecture that I'm going to put online, I'm going to talk about each one of these groups and give you examples of each. So you should watch that by next Tuesday. So next Tuesday, we'll have a little quiz over specifically chapter 2.